hit a point, they deliver a lecture here for our students. This is how we can have an organic relation. So recently I requested them, please deliver a lecture for us. Instantaneously they said yes. That is their greatness. Okay. Both Saisudha Mallur and Babu are PhD from Indian Institute of Science. Later on they worked at TIFR, Mumbai. From there they transited to Western Illinois University, US. They worked very hard and they earned their full-term professor post. Becoming a professor is not easy. So both of them are professors with huge credentials for their CV. So during the course, I request them to give a brief introduction of their CV as well. To Saisudha Mallur and to Babu, it is our pleasure to have you here on behalf of National College and on behalf of Department of Physics, on behalf of the National College, on behalf of APS College and also the Department of Physics of APS College. It's my pleasure and privilege to welcome them. I welcome you, sir. We have with us Professor Jayashree. Professor Jayashree is alumni of National College BASAVANAGUDI for her undergraduate program. Later on, she obtained her MSc from Bangalore University and of course PhD also from Bangalore University. And presently, she is principal of APS College, NR Colony. She has worked in various other government colleges and she has a very rich experience both in research and other activities. So when I requested Jayashree Madam also to collaborate so that in the same campus when they are delivering the lecture, it will reach for more number of people. The madam was very happy. She collaborated with us. Her students are also here. For that, Madam Jayashree, I welcome you on behalf of National College, Physics Department and all of us here. We have Professor Basuraju from BIT, that is Bangalore Institute of Technology, a professor of physics, an enthusiast, physics enthusiast. So he had come to listen to lecture. Sir, I welcome you also. I have from the APS College, my colleague teacher. Sir, I welcome you also. The program is for you. Okay, is for you. I welcome one and all of you for this program. Please make use of it by actively participating. There are two types of participation, passive and active. Passive is, we called, you came, you sat. It is passive participation. Active participation is, you came, you sat, you learned something and you interacted. That is active participation. You are all wonderful students. You will participate actively. I welcome you also. So in arranging this program, Professor Achyuta is working very hard. Achyuta and Mr. Darshan, they are from Department of Physics of National College. I welcome you also, Mr. Achyuta and Darshan. Now, the dais is open to Madam Saisudha and Mr. Babu.
On behalf of National College and APS College of Arts and Science, I welcome Dr. Y.C. Kamla for today's program. Thank you.
Next one. Down arrow, next one. Yes. Okay. And this is the laser pointer. Okay. Hello, good morning. Happy New Year. My name is P.K. Babu. Yeah, it's a pleasure to be here. I would like to thank Principal Kamala and Principal Jayasree for this great opportunity, distinguished faculty members and students of National College and APS College. Thank you so much for inviting us. It's so good to see young students interested in physics, interested in science. First day of the year, early morning, coming here and attending this small lecture. We would like to make it more of an interactive effort instead of us trying to lecture you about what we have been doing. I will try to introduce this topic in as simple terms as possible. I will be asking questions, and please feel free to respond to the questions as well as ask me any questions that you have anytime in between. Feel free to stop us at any part of this presentation. Briefly about me, I did my PhD in physics from Indian Institute of Science here in Bangalore. Then I moved to Tata Institute of Fundamental Research in Mumbai, worked there for 3 years as a visiting fellow. Then went to University of Illinois at Champaign-Urbana as a postdoctoral fellow. Continued to work there as a research scientist. Spent about 7.5 years there, and then took up this faculty position at Western Illinois University. I've been teaching there since 2008, about 16 years. Dr. Mallur also did the PhD from IISc Bangalore, and we have been traveling together, my partner in crime as well as in research efforts. So today we'll be talking about optical properties of rare earth doped glasses. So here is, I will start with acknowledging some of our students. We have a master's program. So many of our students doing MS in physics, they take part actively in research, and some of them complete their master's degree by working on a specific topic, preparing an MS thesis, and they complete it that way. Students from all over the world, Americans, students from Malaysia, Nepal, India, and then so many undergraduate students also. Some part of our work, we usually do the experiments at University of Illinois, where I used to be a postdoc. I continue my collaboration with the Materials Research Lab at University of Illinois at Urbana-Champaign. So after we make some of our samples, we take those samples to University of Illinois to make some measurements over there. So I would like to acknowledge the help and cooperation from the Materials Research Lab at University of Illinois. This is a brief outline of what I am planning to present here. Give you a very brief introduction to glasses and what is the motivation for studying this. Why do we study rare earth doped glasses? What type of experiments that we do, experimental techniques, and the main experimental investigation of the type of systems that we use, absorption of electromagnetic radiation, what we call optical absorption, and how the composition of a glass influences the absorption of energy by that glass. Then we talk about the emission of light from the rare earth ions which are present in the glass materials. So introduction to glasses. Glasses are isotropic. There are two important words that we use in physics, in mechanics as well as electricity, magnetism. One is called homogeneity, and the other word is isotropy. Do you guys know the meaning of those two words? What is meant by homogeneous? Basic definition. Something is homogeneous. Same? That will be time. Homogeneous actually is about space. Okay? If you move from one point to another point in space, if it looks the same, we call it homogeneous. You know, if you have, say, you have taken water in a glass. If you look at one point, one water molecule, it will be exactly identical to one which is sitting in any other point. So if you move from one point to another point, if it stays the same, it is called homogeneous. Isotropic. Isotropic, something, what do you mean by isotropic? Homogeneous one point to another point, isotropic looking same in all directions. That is what is isotropic. So glasses have this unique capability that glasses look isotropic. Any direction that you look, glasses actually look exactly the same in all the directions. This has very important applications for technological purposes. Important aspect of glass, you can make glasses over a wide range of composition. Unlike crystal, sodium chloride you take, it is one sodium and one chlorine. That is its composition. Whereas when you make glasses, Dr. Mallur will tell you, how we make glasses, different types of. You can vary the composition of the constituents over a wide range of possible values. You can do that with crystals. And you can make glasses in various sizes and shapes. You have seen that, glasses come all types of sizes as well as shapes. Variety of industrial and research application. Everyday life, we know that windows, all types of containers, lenses for your glasses. And glasses can be used as host for laser materials. This is where the research that we do play an important role there. Optical fibers used for communication purposes, you can make them out of glasses. Pour me some glass. I know this phrase might sound something entirely different. Pour me something onto the glass, you guys are definitely familiar with that. What do you mean by pour me some glass? What exactly is a glass? Are glasses real solids? What do you guys think? Is glass a solid? Yes, right? You can cut that into whatever pieces that you have. If you have a glass container, it remains as a glass container all the time. For all practical purposes, glasses appear like solids. But I am going to say that glasses are not solids. Glasses are liquids. Glasses are not really solids. What is the main property of a liquid? It flows, right? But have you ever seen a glass flowing? But glasses can actually flow. It can go from one point to another point. It is very, very slow process, okay? Say, for example, you have made a glass window. If you look at very old buildings like 700, 800 years old, such buildings exist, say, if you go to Europe, some ancient churches in Europe, they have glass windows, colored glass windows. These buildings were built about 700 to 800 years ago. Okay, when they were built, these glass windows had uniform thickness all over the place, from the bottom as well as from the top. Now, after 700 years, if you measure the thickness of those glass windows at the top and at the bottom will be slightly thicker. So if you make a glass and come back after 300 years, if you can come back after 300 years, you will find that the size and shape of the glass has changed ever so slightly, very, very slightly, which is the typical characteristic of a liquid. But it is not an ordinary liquid. It won't flow that easily. You know that it takes several hundred years. It is a liquid with very high viscosity. Very hard for it to flow, but it actually does flow. So how do we make glasses? If you look at this particular picture, you can see that you make all the materials, whatever ingredients that you have, melt it, okay? So you have a stable liquid, and then if you cool that very slowly, really, really slowly, then the individual atoms can go sit at regular points and form a crystal. That is what a crystal means. Crystal means it has three-dimensional long-range order. Atoms are arranged at regular intervals at very uniform places. Now, from that particular state of stable liquid, if you cool that glass, that particular liquid so fast, what is speciality of a liquid? You know, all the atoms and molecules are moving around at random. Does anybody know what you call that kind of motion? The name that we use? Things moving at random? That's correct. Very nice. That is called a Brownian motion. Okay? In any liquid that you take, all the atoms, individual components are moving at random. That happens even in this liquid also. So when these things are moving around at random, you take away their kinetic energy so quickly so that you don't allow them to go into regular places and form a crystal. Then if you take away the energy, kinetic energy is basically a measure of temperature of the system, right? At atomic world, energy of a system is nothing but, kinetic energy is nothing but temperature of the system. So you cool the material or you take away the kinetic energy so fast so that you don't let the atoms go into regular places. Then they will freeze in whatever random configuration that you have. That frozen liquid or super cooled liquid is what you call a glass. Understand? So glass is essentially a liquid with very high viscosity. So why do we study these materials? You guys know this. This is your periodic table. So if you look at the bottom of that, these are called the rare earth elements. You have the transition elements over here, and these plus these three are known as rare earth materials. Rare earth materials are very important because, you know, they have very unique photoluminescence properties. The word might sound, you know, a bit intimidating, but you can easily break that down into simple terms. Luminescence means emission of light. You can, you know, get a material to emit light in so many different ways. You can heat something, it can emit light. You can pass electricity through something like a tungsten filament. Electrons will collide with the tungsten atoms, lose their kinetic energy. Tungsten atoms, electrons will get excited to some higher energy state. They are not stable there. They come back by emitting light. So you can produce light that way. So you can produce light in so many different ways. Emission of light by any material is called luminescence. Photoluminescence means if you use one form of light and then get another form of light out of that. Photons are used to produce a different form of luminescence. So rare earth ions, if you use one form of light, like a laser, excite those atoms, then they emit light in different forms. So each rare earth ion has its own characteristic light emission properties. Different colors, different intensities, and you can change the light emission properties of these rare earth ions by playing with the electronic surrounding of each rare earth ion. That is where the importance of glass comes into picture. So glasses can be used for hosting a rare earth ions. You know, glasses can take in anything, small amount of any material that you put in. This is called doping of the glasses. So you can put a rare earth ion into that, and then it is going to be there at a very stable chemical environment. You can excite that using a laser and see the light which is coming out of that. This is the importance of rare earth ions. Now Dr. Mallur will tell you about a typical borate glass, how we make these glasses.
Hello everyone. So thanks for the warm welcome. So I will continue the lecture, what Dr. Babu was talking about, glasses, all right? So you're all familiar with a little bit of chemistry, right? Very simple one. All right, so these glasses are inorganic oxide glasses. So all the raw materials which I am going to make use of in making these glasses, they are in their oxide form. That means they are very stable, they present room temperature and atmospheric pressure. So the type of glasses we are working on are called Borate glasses. You all must have been using some kind of glassware at home for microwave and everything, right, to heat some food. So they are all made of borosilicate glasses. So in this type of glasses, there is no silicates, only borates and other.
The down arrow.
Press down. Oh, okay. So this is the type of glass we are making. The name of this is lead borate glass doped with samarium oxide. So you remember he was talking about the rare earth elements. So out of that, we have chosen samarium oxide. It's a very good fluorescing ion. Okay. He was mentioning the name photoluminescence, right? So another word we use is called fluorescence, because the light coming from these ions are in the visible region. You all know which region is called visible region? Which wavelength to which wavelength? Well, have any idea? Yes. 400 to 700 nanometers. Is that right? You know what colors they are? You know the color of the rainbow? Yeah. So there. So violet. So like that it goes, okay? All the way to the red. These samarium ions, they emit somewhere in the orange region. So when you excite these glasses with some light, so we normally use UV light. You all know what is UV light, right? Slightly lower than 400 nanometers, or approximately you can take 400. So you excite these ions, so they emit light in the visible region of orange region. So the glass will appear orange, okay? So now to make these glasses, we have chosen, so this is called lead borate doped with samarium oxide. So what those numbers are, 30, 69.5, 0.5, these are the composition. 30 mole % of lead monoxide, 69.5 boron trioxide, and 0.5 samarium oxide. So to make these glasses, we have to start using, right? Starting materials. So what kind of materials we can use? So I want in my glass lead monoxide. So these are the materials. So lead monoxide is there. Samarium oxide is there. Boron trioxide is not there. Instead, what do I have? Do you know this compound H3BO3? Are you familiar with that? It's boric acid. Okay, why can't I use boron trioxide directly? Why am I using boric acid? What is the reason? Because boron trioxide is not stable at room temperature and pressure. If you try to bring that boron trioxide, you know that moisture is there, right? All over. It will absorb moisture. It is very hygroscopic. So it turns into boric acid. Whereas boric acid is very stable at room temperature. So we are taking that as a raw material. Okay, so what kind of reactions we are doing? It's a solid state reaction. So we take these raw materials of corresponding composition, and so I will show you what kind of materials we use to prepare these glasses. So let me show in this picture. Okay, the first one. So we are taking the raw materials. So as I told you, lead monoxide, boric acid, and samarium oxide. So you weigh them in the chemical balance and take the corresponding composition and transfer that to porcelain crucibles. You know Chinawares? You all have used, right? Porcelain crucible. It can withstand 1100 degrees Celsius. Such a high temperature it can withstand, because we are going to melt these compound. So for that, the container should be able to hold this material, right? So after we mix these things, we transfer that to a very high temperature furnace. So once you put it there, you heat it to a very, usually we do it around 950 degrees Celsius. That's more than enough for them to melt. Okay? Once you have melted it, next what we do is that it's ready. So do you know the definition of glass? Just now Dr. Babu mentioned, you are basically bringing that liquid to a solid form. That right? You are rapidly quenching it. So what you do is that once you melt this compound, it will be in the molten form. So pour it on a metal plate. So now why do we use metal plate? Do you know the properties of metals, insulators, semiconductors, different types of, you have learned about it, right? So what's the speciality about metals? Why we use metals? Why not insulators? Why not semiconductors? Any idea?
Yeah, they already said, somebody said good conductors.
Ah, okay, that's good. So, sorry, I'm not able to hear because of the echo. Okay, so you pour it, then it immediately absorbs the heat and it brings that material to room temperature. So you have literally frozen the liquid part to a solid part, because the glasses, as definition, the atoms are randomly arranged. Liquids, atoms or molecules are randomly arranged. So glasses are also randomly arranged. So once you quench these glasses, you transfer that to what is called as annealing furnace. Now what is the significance of that? So you remember, we are rapidly quenching, right, from high temperature to low temperature. So a lot of thermal strains are formed inside the glass. It is very fragile. The moment you try to touch it, it shatters. But how will I do the experiment if it's going to shatter, right? I have to make it more stable. So what we do is that we gently take that glass pieces and reheat those glasses. So from room temperature, we bring it to what is called as glass transition temperature. You know, from liquid to glass it forms, right? That temperature is called glass transition. Around 350 degrees Celsius, you heat it. They become slightly soft. When it becomes soft, it releases all the thermal strains and becomes really hard. And then you do slow cooling. Then you take out the glass pieces, you do whatever you want with that. It will be very strong and stable. Now it's ready for the further experiments. So now, before we do that, you know, glasses, it has to be like nicely polished and this thing for any optical measurements. So we use a polishing machine. So we polish our glass samples, and you can see a small piece of glass sitting on that. First, we do what is called as smoothing, because the surface is very rough. So we smooth the samples and then we polish them. That's how all these glasses are made. Initially, when they are made, they are very rough, and they keep polishing it, and then they are ready for. So this is the rough glass and smoothened glass, and finally polished glass. So this shape is very convenient for us to do all the optical measurements. So now the topic will be continued.
Very basic question, why glasses are transparent? Why glasses are transparent? You know, these are very transparent. Why is something transparent?
There are no takers of energy.
Exactly. You know, if you are passing light through that, light is just passing through that, and nothing is willing to accept the light from that. That is why glass is transparent. Okay, any transparent thing for that matter, you know, if light is passing through that with nothing willing to take that energy, no atom, no, typically speaking, to no degree of freedom willing to accept the energy of that external radiation. That is what makes a glass transparent. Is glass totally transparent for the whole electromagnetic spectrum? Visible spectrum, it is transparent. That is why you are able to, it is not absorbing. What happens to the radiation if you try to vary the wavelength of that incoming light? How many of you saw the movie Oppenheimer? You have seen the movie Oppenheimer. Do you remember a particular scene when they're testing the atomic bomb? One person, one of the physicists, he was sitting inside a jeep. Okay, jeep of course has got a big glass window in front of that. His friend is telling him, lot of ultraviolet radiation is going to come. Then he said, glass prevents ultraviolet radiation from coming in. So I am safe inside. So if you look at a glass, it is transparent for the visible region, but it actually absorbs in the UV region. So typical glass, if you look at it, absorption of electromagnetic waves, that is, it doesn't happen in the visible region, but it does happen in the UV region. In BSc Physics, you must have learned about damped harmonic oscillator. Have you heard the word damped harmonic oscillator? That's the simplest model to explain absorption of energy by a system of atoms. That means the incoming energy is being absorbed by some oscillatory system. And since the energy is getting absorbed, the amplitude of the incoming energy decreases. It gets damped. Okay? So that is the simplest model you can use for explaining absorption of light from any system. Transparent, no absorption in the visible region. That means no matching energies for visible region. You know that in the atomic world, energy of any system that you look doesn't vary continuously. If you look at macroscopic world, you are kicking a football, you can impart any kinetic energy to that. Starting from zero, depending upon the strength of your muscles, you can make it as high as possible. But if you are looking at atoms or electrons in an atoms, electrons do not take any kind of energy. You cannot kick the state. They can go only to some specified allowed energy values, which are called quantized energy states, which are available in that particular system. So if you have quantized energy states matching the incoming radiation, then that energy will be absorbed. If you do not have any matching energy levels in that system, energy will not be absorbed by that system. For the visible region, there are no matching energies of the atoms in a glass. That is why it is transparent. But not true at higher energy. Remember, 400 to 700 is visible region. If you go below 400 nanometer, energy increases when you decrease wavelength of the system, right? Higher energy for ultraviolet, even higher for X-rays, much higher for gamma rays. So wavelength is decreasing or energy is increasing. So if you go to higher energies, UV region, energy gets absorbed by the glass. So a typical glass piece, we study the optical absorption using an optical absorption spectrometer. This is the setup that we use at University of Illinois at Champaign-Urbana. Technical name for that is a Carry 5G. For a simple binary glass, if you look at the optical absorption spectrum, remember 400 to 700, this is your visible region. No energy is absorbed. That is why the glass is transparent. But when you go below 400, you can see that the energy is getting absorbed very rapidly. So this is the absorption, extent to which energy is being absorbed by that particular system as a function of the wavelength. You can see that why glasses are transparent. What information do you get if you look at a graph like this? Any useful information? If you look at a graph, what does it tell you? Nature of the substance, that is correct. Can you be a little bit more specific? if you look at the numbers on the x-axis and the y-axis, what information is giving you? Absorption is nearly zero for some time, and then it suddenly starts picking up, right? So the place where it starts picking up the absorption would correspond to, as Professor mentioned, some matching energies in that particular system. So what are those matching energies in that particular system? That information is actually contained if you look at this. So this is where the glass is going to heavily absorb that energy. Technical name for that is absorption edge. Nothing is being absorbed, so it's all flat. Then you come out of that particular flat region, like if you are coming all the way here, no absorption, but from here, you are suddenly jumping. You call it an edge. That's exactly the same word we use here. This is known as the optical absorption edge of the glass. Above the edge, glass is absorbing energy heavily for that particular energy or greater than that. So that information is very useful. That tells you something about this structure and electronic property of that basic glass. Absorption edge is known as the optical band gap. Above that gap, energy will be continuously absorbed by that particular glass system. So what happens to the optical absorption if you try to change the glass composition? What I showed was for a specific composition of the glass. So here, this is a series of lead borate glasses. Dr. Mallur showed you that, if you have 30 mole % of lead oxide, you keep varying the percentage of lead oxide in that glass. You can see that the optical absorption edge changes. As you go to higher and higher amount of lead, the glass absorption edge is shifting towards lower and lower energy. Higher energy means the gap is higher. Lower energy means the gap is getting smaller and smaller. So when you increase lead oxide, the optical absorption gap decreases as a function of glass composition. The same graph, what you have on the left hand side, is redrawn here. If you guys remember the equation, energy is as a function of frequency, typical E equals some constant times the frequency. Do you remember the formula? H. H is what constant? Planck constant. Yeah. So if we use that simple equation, the wavelength information can be converted into energy in electron volt. So it is the same graph that you have on the left, but plotted as a function of energy. And then if you draw an intercept for each of these lines, whenever that touches your x-axis, energy is given here in terms of electron volt. That tells you exactly what the band gap of that material is. So this particular experiment tells you how the optical band gap varies as a function of glass composition in a typical binary system of glasses. So those band gap information plotted as a function of the glass composition is given here. This work was published in the year 2015. A lot of our students, both graduate and undergraduate students, were involved with this particular work. Next, we will go on to the other optical property that we look at this glass. I use the word photoluminescence. Dr. Mallur said fluorescence. Basically, they are the same. Okay. So this is the block diagram of a fluorescence spectrometer that we have. So you have to have a source of light which can be used to excite the rare earth ions, so that we use a laser, typically about 4 or 5 nanometer, which is very much violet, very close to UV, but you can still see that, or a green laser that we use. That laser light will be falling on the glass sample. Can anybody tell me why the glass sample is placed in that way, that particular orientation? 45 degree, right? Why is it at 45 degree? Because you are looking at the reflected light from that. Okay, we are not looking at light which is transmitted. we are looking at the reflected. So if this is your glass surface, okay, light comes here and then it gets reflected. So whatever rare earth ions that you have in that surface few atomic layers, they get excited and they emit the light, and you want to see the light which is emitted by the glass sample, that is going to be collected to analyze. Now, when you have a laser falling on this, part of the laser also gets reflected. Okay, and laser is very powerful source of light. You don't want that to go into your detector unit. So you use a small laser filter, cuts off the incoming laser, but allows all the other light to be transmitted through that. Very simple idea of using a filter here. Then you have some couple of focusing lenses. Generally, we use either a charge coupled device or even a simple diffraction grating. In your optics class, you have learned about gratings, right? Grating, you know, a glass plate or a film with large number of lines, very narrow slits through that. Light undergoes diffraction when it passes through small gaps. And the extent to which it gets diffracted depends on the wavelength of the light. Simple, you know, you have d sine theta equals n lambda, if you remember that equation. So different wavelengths will get bent in different angles. That is how a composite light is split into its components by a diffraction grating. Then if you have a photomultiplier tube, that means some device which can count the number of photons coming at each wavelength and then plot that as a function of wavelength, you get a spectrum out of that. That is a very basic idea of recording a simple fluorescence spectrum from any material. So that job is done by a computer. So this is the block diagram. This is the actual diagram of the setup. So you have a laser, which, you know, the laser light itself is not easy for you to see. And then a glass sample is kept, remember, 45 degree. And then the reflected light, there is a laser filter which will chop off the laser. Some couple of converging lenses, convex lenses, that will focus that onto a small gap over here. And then you have set of gratings and a photomultiplier tube that will count the number of photons coming at each wavelength, and the computer will give you a spectrum like that. This is a simple fluorescence spectrum from the samarium ions in our glasses. Again, fluorescence emission from samarium ions. You know, when you are doing this kind of experiment, lab has to be under total darkness, because if you have any external light source, those lights will also enter into your detector, will spoil the information that you have. So experiments must be done under complete darkness. So some more information, more technical. If you look at, I told you, if you look at the energy levels, these are discrete quantized energy levels that exist in a rare earth ion. This is the energy level diagram of a simple samarium atom that you have. So we use a laser at 488 nanometer that can excite the samarium ions. Excited levels, lifetime is short, and then some of the atoms from the excited level, they will come down to a ground state without actually emitting any light. This is through collisions or thermal relaxation. All of them get accumulated over here, and from this stage, this particular energy state, they can come down to various ground states. If it is coming to this ground state, the emitted light will be green in color. If it is coming to this state, you will get red in color. Any of the other two states, it will be, this will be orange in color, these two will be red in color. You can see that the corresponding emissions, 4 lines, they correspond to these 4 transitions that you have. So how does the fluorescence of a typical samarium doped glass vary as a function of glass composition? You can see that all of them have the same basic pattern, but the intensity of the light coming from different composition is different. Even though the absolute intensity doesn't make any real physical sense, because absolute intensity would depend on strength of the light that you use, the extent to which your detector has been biased, so many things. But if you make all the glass pieces, record the spectrum under exactly identical conditions, then you should be able to create a stack plot so that you will be able to compare their intensities. That is what we have done. These are all that different 4 transitions that you have in the system. One, this is going to get a little bit technical. Why we do this? We try to understand a particular quantity known as stimulated emission cross section. I'm going to use. Yeah.
So here this observation with a variation in concentration of
Lead oxide.
the emitted light is also differing.
That's correct. Yeah.
You are sending the laser of high intensity and
Yeah, the same laser is used for all of them. Yeah.
okay. This is the crux.
Yeah, this is the most important part. How the glass composition influences the nature of the light which is coming out of that. Okay. Remember, I told you, if you look at samarium, you have discrete energy level diagrams that you have. Okay. The energy level diagram for a given samarium depends on how the electronic surrounding of that particular samarium is determined. What all things are sitting around that? How many molecules of lead oxide are there? How many molecules of boron trioxide are there? And in what orientations they are sitting? Because remember, at atomic world, everything is interacting with everything else. If you use quantum mechanics, wave functions of atoms, they are all overlapping with each other. The extent to which they overlap and how what we call the technical term that we use is crystal field, the electric field produced by surrounding charges and surrounding electron cloud, they all vary as a function of the glass composition. That variation will be reflected on the light which is emitted by the samarium ion. Excellent question, Dr. Kamla. Okay. So that variation is what we are seeing as a function of the glass composition. You can see that there is slight shift in the peak position of each peaks, and there will be variation in the width of the peak. And technically we use what is called full width at half maximum. If you have any Gaussian profile, that is a quantitative measure of the variation in that Gaussian profile. So we look at this particular quantity, sigma p. Basically, it represents the probability of a stimulated emission transition. Okay? How easy or how hard it is for a samarium ion to emit after it gets excited. So that decides the intensity of the emitted light which is coming from that. If you want to have very good emission, it is preferable to have a larger sigma p value. That's an essential requirement for our practical applications. This depends on the bandwidth, width of that particular line, radiative transition probability, another quantity that we calculate from optical absorption, and the refractive index of the glass. What is the refractive index of a material? Yeah, ratio. Yeah, the definition. I know. So glasses, it is like, yeah. It is the ratio of the velocity of light in that, yeah. So velocity of light in vacuum to velocity in that particular medium. Because in most transparent medium, light slows down. That is why most materials refractive index is more than 1, right? For air, it is approximately equal to 1. And then if you glasses, if you took 1.5, 1.6, will be the refractive index of that. So the refractive index, you can vary by varying the glass composition. So another parameter that we try to play with is the refractive index of that glass.
And for this particular glass, these are the range of 1.9.
1.9. Yeah. Bismuth borate glasses. Yeah. 2.5, we have glasses with 2.5. Why diamond shines, since she mentioned, about diamond. the importance of refractive index. Why is diamond so shiny? Yeah, higher refractive index. Exactly. The total internal reflection happens at very, very small angles. Anytime you exceed that, light is getting totally reflected internally from that material. Diamond itself doesn't produce any light. It is just the light which is reflected from that. That's the price you pay for diamond, for that reflection. For that high refractive index is all the money that you pay for. Okay? Diamond's high refractive index is very important in producing the total internal reflection. So like that, our idea is to improve this particular quantity known as stimulated emission cross-section by playing with the composition of the glass. So we have seen that, deriving this quantity takes a lot of time, analyzing all the optical absorption, fluorescence with a lot of computer programs. So we show that with the lead oxide concentration, you can see that there is a peak in the stimulated emission cross-section. So particular value of the composition, the glass is most efficient in producing fluorescence light. So that is, one of the most important conclusions from this particular work that we have done. So optical band gap, the first quantity from absorption, you can vary that with glass composition, and you can use the glass composition to change the stimulated emission cross-section of rare earth ions. So with that, I'm going to conclude, but feel free to ask me any other questions that you have on this subject. I will be happy to, me or Dr. Mallur will be happy to answer your questions.
So from the graph that the previous displays the lead oxide composition, variation of lead oxide composition and the emission, it is the lead oxide that primarily influences the
Rare earth ion.
rare earth ion.
That's correct.
So that is the king.
Yeah.
So by changing the structural groups around the rare earth ion, how can we change by changing the composition?
Yeah. You can do that with a crystal, because crystal has a definite composition. Yeah.
So most of the time it is 0.5 only, samarium.
Yeah.
Because
Yeah, that's an
0.5 samarium fluorescence, when you compare with 1 mole percent or 2 mole percent, there's a thing called fluorescence quenching. That is, one samarium will fluoresce, the other one will absorb if more samarium ions are there. So that is why we reduce the number of samarium ion in the sample. So
optimum. That's right. Yeah. Yeah.
So 0.5 is optimum.
Yeah.
optimum.
You can do fluorescence with 0.1, 0.2. We have done even with 3%, 3 mole percent. But that much of concentration of rare earth ions will kill the fluorescence of most of the neighboring ions from that.
Fluorescence is going to be
Decreased when you go to very, very high concentration.
what we need, it is not going to be shown.
Yeah. That's right.
With this lead oxide, because you have taken samarium at concentration of 50 mole concentration, its efficiency is maximum.
Yeah.
And it gives you orange light.
Yeah, it does. It does.
So you can design the molecular composition for various colors.
Colors, that's correct. Yeah.
There is one thing. Samarium ion, in general, you saw that there are 4 transitions, right? And when you combine all of them, it's going to give you a single color, orange color. So it is
For the naked eye of a person.
Okay. That means the orange is dominant.
That's
Rest of the
correct.
colors are submissive.
for that ion.
Yeah.
If you use a different rare earth ion like neodymium, you will get a purple color. If you use dysprosium, you will get green color. So by changing the rare earth ion, we can change the color, emission colors.
Yes, that's where it has large marketability.
That's correct. Yeah.
Display purposes.
Display purposes, marketable.
Yeah.
So is the same technique and other things. Nowadays we have the so-called synthetic diamonds. Synthetic diamonds. They are available in market.
Yeah.
So the 1 carat diamond, which costs natural by 14 lakhs, is 1 lakh in this. So that's altogether a different one.
basically diamond is carbon. Okay, but you can create that under high pressure, high temperature conditions. That is how you create, artificial diamonds. And then you don't have to wait for hundreds of years where Earth is making that for you. That is how they have been able to reduce the price of the diamond when you use external machinery for converting graphene, carbon into diamond.
In the interest of the vector model, the transition that you have shown, the 4G 5/2
Yeah.
to 6H 7/2, can you slightly elaborate?
Okay.
Yeah, just go back to the previous one.
Oh, okay, yeah. I will show you the energy level diagram. Yeah. Yeah.
Okay. So, that is the, if you are asking those energy levels, say for example, samarium ions, can you figure out that electronic configuration
Yeah.
on the top?
This one we need. The spectral lines.
Yeah.
That's it?
Transition lines.
Because they have it in syllabus,
For the vector atomic.
Yeah.
model, I want them to go through application orientation. You can enlarge profile.
Yeah.
Image can be enlarged.
ಇದೊಂದು
ಇಲ್ಲೇ ಮಾಡ್ಬೇಕು.
Oh, like that. Oh, the other one. This one. Yeah, this one. Okay.
So you are asking.
Yeah. How do you get the the spectral terms?
That's what.
Yeah.
Talk about that.
Is fine. Okay.
So you are asking about the spectral terms.
Yes.
Okay.
She is asking about the spectral transition, the levels which you have shown,
Yeah, from that 4G count level to 6 level.
SPD, FP,
Yeah, that's right, that's right. Because.
So you find the total angular momentum and you find the total spin.
Yes.
Then you add those two.
Yes.
J plus S to get the J.
That is the J level that we are doing.
Yeah.
J and then G.
Yeah.
Yep. So that means L equals SPD. So L equals 5.
ಎಷ್ಟಿಂತ ಮೇಲೆ ಹೋಗಿದ್ದಾರೆ.
Yeah.
So that's why they are getting
These four are speed states. Only in G you have. And the two in G, 5/2. Yes. And then
Okay, here one thing I would like to mention.
he has to follow all the action rules.
Samarium ions have 6 electrons in their F shell.
Yep, yes.
Okay, so now a samarium atom. Samarium ion means 3 electrons is removed. That's how they form bond with the oxygen.
Okay.
So they have now 3 more electrons in the F shell.
Yes.
So electron-electron interaction. So that is why we get so many spectral terms.
Yes.
Yeah, that's what you are seeing. And you are observing the transition between them.
In the gas phase of the samarium, you will not see any of these transitions. Because all the energy levels are what we call degenerate. They all have the same value. Only when you put samarium in the glass solid form, the local interaction with the local electric field splits the degeneracy so that you will be able to see all the transitions. So that is why we need glass.
This is the beauty of visualization. That is the beauty of physics. Okay. Sir, Basuraj sir. Please.
You told that, gas doesn't absorb anything.
In the visible region.
Visible range.
That's right, yeah.
But have you studied the emission spectrum of glass so that it should not have any emission of electromagnetic waves in the visible range?
It doesn't have in the visible region, yeah. So if we heat it up, you will not see any light emission from pure binary glass.
Okay.
Okay, but if you dope that with rare earth ions, it will emit at that time.
Then it introduces.
So if you look at, the glasses that you are wearing or I am wearing, this will not emit any light in our visible region. That is why it is totally transparent.
Basically, it is inhomogeneous material, sir.
They are homogeneous material. Not in the atomic level.
Okay.
Atomic level, of course, the composition is going to be very different. But at the macroscopic view, glasses are homogeneous materials. They look the same everywhere.
They are isotropic also.
Yeah, they are isotropic. Those are very important properties. They will influence emission of light from rarer ions from that.
Have they studied the emission spectrum? Is it a continuous range of
No, discrete ones.
discrete?
Discrete, yes. There will be characteristic peak of the emission spectrum coming from that.
Thanks.
You will observe fluorescence not only in the visible region, even in the IR region
IR.
also you will see. But only thing we can't see visually, but the spectrometer will detect the transition. So you can observe.
So 4G 5/2 is metastable.
Yeah, that's correct.
The rest are
Yeah.
wherever
Yeah.
it goes.
Yeah, from there it,
So everything comes to 4G 502, and from there it makes, further.
because the
transition.
energy difference is so large, it cannot come out as heat. It will come out as light.
How does the
Those
electron
colors
go?
corresponds to your concentration. Green, orange,
No,
or all
right
the
now
four are
this is
possibilities.
one particular
This is one atom.
concentration.
Yeah.
One concentration, all four are possibilities,
present.
but together it appears orange.
Orange. Yeah.
The intensity of orange is more.
That's correct. 598 is the maximum intensity.
That is the probability of transition is more in orange.
Orange region.
Rest is less. So let us not go further. Why so?
Well, you have to come up with the overlap integrals to get the calculation of probabilities. That is true.
This is really beautiful. Okay. If you have any question, yeah? You have a question?
Any questions, any doubt?
Sir, ಅದು ಕಾರ್ಬನ್ ನ್ಯಾನೋಟ್ಯೂಬ್ಸ್ ಡೋಪಿಂಗ್ ಮಾಡಬಹುದು.
Carbon nanotubes? No, I don't think so. I mean, you are talking about whether we can dop the glasses with carbon nanotubes?
Yeah, instead we have used semiconductor
We can create nanoparticles inside the glasses. That we have done. You can grow semiconducting and metal nanoparticles inside the glass. That was actually, part of another talk, but due to time limitation, I did not go into that part. Nanoparticles can be grown inside the glass.
See, the initial sample preparation, I talked about just lead borate glass with samarium oxide. So the starting material we add like cadmium selenide, zinc selenide, they are all, they can form nanoparticles. So you melt them and then you quench it, and we do what is called as controlled
Annealing.
dissipation annealing. So then you can grow the nanoparticles in. And that will affect the fluorescence of rare.
I'm just trying to see whether I can show you one transmission electron micrograph.
You can show back that
Yeah.
nanoparticles.
So these are, glasses with nanoparticles inside that.
You can see that small black dots. So by using transmission electron microscope, you can see all those nanoparticles formed.
So it's a simple 1 nanoparticle you can image. You can see, the layers of zinc selenide molecules sitting in that with high resolution image of that.
Okay, thank you. And now I request So I request our President, Dr.HN Subramania, is President of National Education Society of Karnataka, and our So I wonderful example for perseverance and commitment, whatnot. Okay. He is 93 years younger.
93 years, still young.
It is young only. Sir, come in. ಮುಂದೆಗಡೆ ಸೇರಕ್ಕ ಆಮೇಲೆ ತೆಗಿಯೋಕೆ. ಇನ್ನೊಂದು ವೇಟ್ ಇದೆ. ಅಚ್ಯುತನ್ ಕರೆಯೋಕೆ ಹೇಳಿದ್ದಾರೆ. ಅಚ್ಯುತನ್ Now I request all the dignitaries to felicitate our speakers of the day. Please come.
Respected dignitaries on the dais and off the dais, dear students from National College and APS College of Arts and Science, and the faculty members of Department of Physics from both the colleges. It gives me an immense pleasure in proposing vote of thanks for today's wonderful program. What else you want on a New Year day, that's on 1/1/2024. This is a wonderful gift that one can give to their students. So with this, I would like to thank the Professor Saisudha Mallur and Professor Babu for giving a wonderful talk on the preparation, synthesis, and characterization of glass. And the talk was extremely useful for all our students, and it has not only thrown insight to the world of glass, but also made our students to pursue their career in physics. This is a wonderful gift that you have given. The fascinating couples, both of them, they shared the dais and they made our students and also us to cherish today's moment. Thank you, Saisudha and Professor Mallur, Professor Babu sir, and I would like to thank the President of National Education National Education Trust, that is the National College, Dr.HN Subramanian sir, for giving this opportunity to organize this type of joint venture. Thank you, sir. I thank Shri Krishna Gowda sir, GC Chairman, the National College. GC member for providing us this opportunity to, especially on the New Year Day, to organize this type of program. Thank you very much, sir. I express my sincere thanks to Dr. Y.C. Kamala. She is one of the dynamic principal. She is doing in all dimensions for the improvement, for the upliftment of the college, for the welfare of the students, and the Bangalore, southern region area of Bangalore identifies our in-depth knowledge, our in-depth dedication, and I thank Dr. Y.C. Kamala for doing this type of program. Thank you, and I wish you to achieve and to fulfill all your desires, dear Professor Y.C. Kamala. And finally, I thank our dear students, though the number is less, and on the New Year Day, you all come all the way from APS College to National College. This shows your love and passion towards the subject, as you all studying two subject formula, that is, most of you are from physics and mathematics background. Without having the chemistry background, you could be able to learn this subject and you have enjoyed this session. I thank the students from the National College BASAVANAGUDI and also APS College of Arts and Science. And one more person, if I go wrong, if I am not going to mention his name, Dr. Basavaraj is a physics enthusiast. He has come all the way to listen to this talk. Thank you, sir. Thank you for showing so much of interest to physics. I thank each one of you, the teaching, non-teaching staff of the National College, for supporting this program to happen in a most fascinating way. Thank you one and all.
Thank you, everyone. Coffee is arranged. Please have coffee and immediately disperse for your classes. Okay? It is exactly 12 now. Within 5 minutes you finish your coffee and go for classes.